Hey everyone, let's talk about scattering matrices. So remember, we've introduced this idea of an n-port microwave network. Okay, so what does that mean? Well, take something like your nano VNA here. You notice it's essentially a black box with two ports on it, right? So you could describe this as essentially a two-port microwave network. Okay, I could excite this port here with some voltage, and something may or may not happen inside here to give me a voltage and a current out over this other end. And vice versa. I could excite this port, something will happen inside, and a signal will come out one of the other terminals here. So this idea of a microwave network is just kind of this notion being extended out to n ports. And you just imagine a black box where I don't necessarily know what's inside of it, but I want to be able to kind of describe it in a high-level sense. So one of the first things we came up with was this notion of a generalized impedance matrix, right? So I could have a voltage over here relative to some current over here. But remember that each of these voltages is actually comprised of a forward and a reverse propagating wave, right? So I'm going to write, say, the nth voltage here. So say this is terminal number n. There is actually a forward propagating wave or signal plus some reverse propagating voltage. And likewise on the current, there's this forward propagation plus, and then a reverse propagation, which we described with the negative sign because of the current in the other direction. So more broadly, you imagine all of these little two-conductor transmission lines. There's a positive and a negative, and there is a forward propagating signal here, and then a reverse propagating signal there, right? Because, for example, this n-port network could just be nothing but a bunch of open circuits, so I could just have a bounce coming in here, or they could all sort of tie together where a signal comes in here and it will spit out all of the other direction, all of the other ends. So you have to remember there is a forward and reverse propagation on each of these signals here. So that this is forward goes in and then the reverse comes out. And remember also, we had to define that terminal plane for a phase reference on each of these lines there. So you would say this is terminal plane 1, terminal plane 2, so on and so on. So it's one thing to talk about just the voltage relative to the current, but many times we're more interested, in fact, in my experience, more often than not, we're far more interested in describing the voltages in terms of an excitation at one port. Say I have a signal coming in, what voltages will come out of the other terminals? That, in my experience, is actually the far more interesting question in the more broad, generic sense. So what we're going to do is just define a metric of that, and it's going to be called a scattering element, like so. Scattering element is defined as the following. I'm going to say S sub ij is defined as, so this is a true by definition because we say so, is going to be the reverse propagating voltage from the ith element divided by the forward propagation going into the jth, subject to the condition that V sub k is equal to 0. So all other excitations are 0 except for obviously j. So I'm exciting the jth port. All the others are not being excited. So you imagine one signal coming in here, but all of the other input signals are 0. So I'm just exciting the one, and then I'm measuring, say, the exiting signal over here. So this would be my j in this case, is the one being excited. And then this is my I over here, and the ratio of that input to that output is my scattering element. And hypothetically, if I excite this port, I might even have signals coming out of all the others, which I would then define in terms of just different indices. So in the broad linear sense, all of this stuff should obey the principle of linearity, right? So we can describe this as a linear system because circuit theory is fundamentally linear, meaning essentially the whole is nothing more than the sum of all the parts. So that means in the broad sense, I can just describe this as a matrix vector or a matrix vector equation, which is another way of saying it's a linear system. So I'm going to say V1 minus V2 minus dot 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 V sub n minus. So it's a vector of the reverse propagating signals. And we're going to define this whole matrix here, S11, S12 dot 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 S1n. And then we'll say S21, S22. Sorry, I didn't quite align my rows here. S2n dot 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 dot. So this is n by n. It could be 50 by 50 for all we know. So we'll go all the way down to S sub n1, S sub n2 dot 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 S sub nn. And this guy here is called the scattering matrix. So I'm going to denote it with the double bars here. This, of course, will be my, I guess, reverse voltage propagating vector. And then over here, I have all of my excitation, or my forward propagation. V1 plus, V2 plus, dot, 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 all the way down to V sub n plus, which we will simply write as V plus. Okay, so we have a nice, simple matrix vector equation of the form V minus is equal to my scattering matrix times V plus. Okay, so there's nothing really physical happening. This is just a definition of a particular performance metric for some microwave network. And you can think of a lot of real-world examples where this might be particularly interesting. Say, for example, here is an antenna, and it is broadcasting. Okay, so this would be my V plus over here. I'll say VJ plus. And then over here, I might have another antenna or 2, or 3, or 10. Okay, and there's going to be a V sub, say, I minus, and there's going to be a V sub K minus, right? So that energy is going to be exciting here and meander its way down to here and manifest as, you know, kind of an exiting voltage here. So you notice that black box doesn't even have to be like a physical circuit box. It can just be an array of antennas. And the same principle will apply, and this will allow me to characterize how much energy is, say, going from one antenna to the next. Another very simple example, you've probably seen this in your circuits labs at some point, is a simple BNC T connector. And unfortunately, I don't have any in my kit, but it's you know, a little connector that looks like this. And let's see if I can draw this kind of like that, like so. Okay, and there's a little inner conductor there and an inner conductor there. Okay, and you can simply, you know, plug a BNC or a 50 ohm cable into that using BNC connections. And I could excite this connector with some positive voltage here, and you can imagine some signals coming out the other end and maybe even a little bit reflecting, right? So this scattering matrix is just a nice sort of handy tool for describing what would happen in this particular circuit. And given a particular circuit, I can in turn create a scattering matrix that corresponds to it and describes its behavior. So that's the fundamental essence of what a scattering matrix is, and we'll do some examples to help solidify that when we do our lectures in class.